Go ahead.
Okay, welcome to a new session of this Latin American seminar on set theory called Seminario Colombo-Mexicano de Teoría Conjuntos. Today we have a special speaker and excellent mathematician. He is Professor Justin Moore. He works at Cornell University in USA, and his field of expertise is set theory and its application in several topics of mathematics. Then thank you so much, Professor Justin Moore, for accepting our invitation to give a talk in this Latin American seminar. We are so happy with your participation, and we can start with your conference. Thank you, Professor Justin Moore.
Okay, yeah, thank you for the invitation. And I would say it's good to be here, except here is in fields and not in South America, but well, or Mexico, but some other time. Okay, so I want to talk about some joint work with James Cummings and Todd Eisworth. All of this is in one paper, which is a preprint on the archive. The details are there. The work was supported in part by the USNSF. So I want to just sort of begin with two theorems, and I'm going to spend probably the better part of the hour just giving some historical background to the two theorems. And then I will talk about roughly how to prove one of them, and then wave my hands and say that the other one can be proved in a similar way. So the two theorems I want to talk about, one of them is, let's see, call it theorem A, assume diamond. So this is Jensen's diamond principle. Then there is a countryman line which is minimal. And then this is, I'll get to what I mean by that in a second. The second theorem, B, is assume square with built-in diamond at a cardinal kappa, then there is a linear order of cardinality kappa plus, such that L is, well, which is, I should say, minimal with respect to not being sigma scattered. Okay, so let me sort of explain what some of these words mean, and maybe remark on what this principle is a little bit. So when I say minimal, I mean with respect to the relation of one order embeds into another order. So in the first theorem, there's a countryman line with a property that it embeds into all of its suborders, which are, say, countrymen, or which are uncountable, which are, this is the same statement, right? So of course, the countryman line can't embed into countable suborders, but it embeds into all of its uncountable suborders. And this is just using Jensen's diamond principle. So the second theorem says assume this so-called diamond with or square with the built-in diamond. So this is a principle, right? This is a principle that holds in if V equals L. It's something that you can force with a relatively nice forcing, and if you know what square says, it's a square sequence, sort of working together with a diamond sequence, right? So the diamond sequence that is associated at each, at each ordinal, that has some coherence properties that mesh well with the square sequence. And it's not completely trivial to write down what this is, but it's a little bit lengthy to write down the full definition, but it's in some sense what it means exactly is not terribly important. The relevant information is that it holds if E equals L. It's something which is an L-like kind of principle that is combining some sort of a coherence property or coherent sequence with a guessing principle. And here it's saying that there's a linear order of arbitrarily large cardinality. So if E equals L, there are any cardinal which is any cardinal kappa, let's see, which is will have the property that square sub kappa holds. So every successor cardinal will have a linear order associated, of that cardinality, which is minimal with respect to not being sigma scattered. So this means that any suborder which is not sigma scattered contains a copy of this order. In particular, any suborder of size which is properly less than kappa plus is sigma scattered, right? Because the linear order can't embed into a smaller suborder. It also tells you, in addition to that it embeds into all of its suborders of size kappa plus, which are not sigma scattered. And this particular order is a kappa plus Ehrenstein line, which I'll get to what that means later. And in fact, a kappa plus Countryman line. Again, whatever that means. So the proofs of these two results are actually, in spite of the fact that they sound different, they're closely related. And I'm going to focus, to the extent that I'm going to give you any proofs, I'm going to focus on the proof of this first statement, because I think the key ideas are already there. And that's something that you can understand. And if you want to go further and understand the second theorem, well, you can look at the paper, and it shouldn't be too difficult. I should also pause to say, if anyone at any point in time has a question about something I say, or that there's a set theoretic assumption that you would like me to state or elaborate on what it means, or just clarify some definition, just speak up. I don't have a good view of who's logged in. I pretty much can just see my screen, so just unmute yourself and interrupt me. Okay, so the basic definitions: a linear order L is scattered if the rationals do not embed into L. And L is sigma scattered if L is equal to a union of Ln, where each Ln is scattered as a sublinear order. So this is L is a linear order here. Right, so notice that well orders and converse well orders are scattered, and a lexicographic sum of scattered orders is scattered. So by that I mean, if you have a linear order L, and you sum over x of L, or x and L of L sub x, where there we go. This is if L and all LXs are, right? So this, what does this mean? It means that I take a new linear order, which is a disjoint where the underlying set is a disjoint union of the LXs, where LX are each linear orders. And you order everything in a single LX in the way that LX tells you to order it. And if you have something in LX and something in LY, and X is less than Y, then you put everything in LX before everything in LY. So Hausdorff showed that the scattered orders are smallest class with these two properties. In fact, I think he showed something a little bit stronger, which is that if you just take sums over well orders and converse well orders of orders that you know are orders that you know are scattered, then the result builds up the entire class of scattered orders. And as a consequence, if L is scattered and the cardinality of L equals kappa is a regular cardinal, then kappa embeds into L, or kappa star embeds into L. So we'll come back to that later. And what are examples? Okay. I guess that's all I want to say about Hausdorff. Lever kind of, there was a question due to Frise of whether the countable linear orders were what's called well quasi-ordered by the embedding relation. That is, if you have an infinite sequence of countable linear orders, is there an earlier one that embeds into a later one? And Galvin suggested to Lever that he might even try to prove this for the class of sigma scattered orders, which I defined earlier. And I think that the class of sigma scattered orders was not really well studied before Lever. But Lever proved that result, right? That the sigma scattered orders are WQO if Li, I, and omega are sigma scattered, then there exists an I less than J, Li embeds into Lj. A result of this is quite nice because it tells you that this is equivalent to saying that there are no infinite antichains in the class and there are no infinite descending sequences. So if you have a hereditary subclass of your orders, the things which lie outside of it are governed by finitely many sort of forbidden configurations, right? There are finitely many orders that live outside, such every other one is larger than one of these finitely many. So a consequence of Lever's result is that the scattered orders are well quasi-ordered, and also that the countable orders are well quasi-ordered, right? The sigma scattered orders both generalize the scattered orders and the countable orders sort of simultaneously. So what are examples of orders that are non-sigma scattered? And just maybe so any set of reals which is uncountable. So going back to Hausdorff's theorem, that this consequence of Hausdorff theorem that if you have a scattered order which has cardinality kappa, which is a regular cardinal, then either kappa or its reverse embeds into L. This immediately extends to sigma scattered orders. So if you have a sigma scattered order, at least one which is say uncountable, then either omega 1 or omega 1 star embeds into L. And we know that omega 1 and omega 1 star do not embed into the real numbers. So any set of real numbers which is uncountable is not a sigma scattered order. And another example, which is sort of less obvious if you're not a set theorist, is, let me just do it this way. In the Ehrenstein line. So this is an Ehrenstein line is you can ask, is there a linear order which it doesn't contain an uncountable set of reals, it doesn't contain omega 1 or omega 1 star, and yet it's uncountable. And so in fact such orders exist. And there's a natural example of such a thing, which I'll mention, is that suppose that you have E beta less than omega 1 is such that E beta as a function from beta to omega is finite to 1. For all beta. And 2, if beta is less than delta, or sorry, beta is less than gamma, then E beta is equal to mod finite E gamma restricted to beta. So this is coherence. Then the E betas lexicographically ordered is Ehrenstein. In fact, this collection has a stronger property. Are an example of a countryman line. An uncountable linear order C such that C cross C is a union of countably many totally ordered subsets. Right, so countryman, I don't really have time to go into this, but countryman implies Ehrenstein. And it's also true that, well, countryman orders are inherited under taking suborders. It's maybe worth remarking, even though this is not a major part of the story, is that PFA implies that any Ehrenstein line contains a Countryman suborder. So these, in some sense, are a typical example of an Ehrenstein line. I mean, well, there are special class Ehrenstein lines, but they are good examples in that they're kind of basic examples of Ehrenstein lines. So this is another example of an order which is not sigma scattered. Again, they can't contain a copy of omega-1 or omega-1 star. And so by Hausdorff's theorem, or that modification of Hausdorff's theorem, they can't be sigma scattered. Now, you might ask, well, there are always real types, you know, ZFs, so real types and Countryman types exist in ZFC. Are there minimal examples? So Dushnik and Miller a long time ago showed that under CH, there are no minimal real types. And Baumgartner, even though this isn't how he originally phrased it, it's sort of how we usually think of his result today, is that PFA implies that any set of reals of cardinality LF1 is minimal with respect to being an uncountable linear order. Or for that matter, for the presence in the context of this talk, it's minimal with respect to being non-sigma scattered, right? For a set of reals, those two things are the same thing. Now, this is sort of the two natural results for reals, sets of reals, real types. For Ehrenstein types, the story is a bit more complicated. Abraham and Shala showed, so to assign dates to these, this is Dushnik Miller is, I think, sometimes in the 40s. Baumgartner's result is in the early 70s. Abraham Shala is the early 80s. Abraham Shala showed that PFA implies that any Countryman line is minimal. And in fact, you need less than PFA. I think MALF1 is sufficient for this result. If you have the full strength of PFA, or rather PFA for posetsets of size LF1, you can prove a bit more. You can prove that if you take any two Countryman lines, then they're either bi-embeddable with each other, like each one embeds into the other one, or each one embeds into the reverse of the other one. Countryman lines have this property that they cannot embed into their reverse, so this is sort of optimal. Separately, I proved, let's see, this was around, I think 2007, 2008, something like that. I think it was published around 2008, but maybe proved a bit earlier, that it is consistent with CH and not diamond for that there are no minimal Ehrenstein lines. That is right. No, there are no Countryman lines which are minimal, and they're not even Ehrenstein lines which are minimal that are sort of non-Countryman. Now, I guess there's sort of one other result that I want to mention here, and that's oh, sorry. Actually, that's getting ahead of ourselves. So this kind of gives us some picture, right? This model also satisfies that omega 1 and its reverse are the only linear orders which are minimal with respect to being uncountable. All right, so omega 1 embeds into all of its uncountable suborders. In fact, it's isomorphic to all of its uncountable suborders. And omega 1 star embeds into all of its uncountable suborders. In fact, it's isomorphic to all of them. But under PFA, a Countryman line is minimal also. Its reverse is also a minimal uncountable linear order. A set of reals of size aleph 1 is a minimal uncountable linear order. And you can wonder, is there a ZFC example of a minimal uncountable linear order, which is something other than just sort of the trivial ones, omega 1 and its reverse? And by Dushnik and Miller, they can't exist. There are no real types which are minimal in the presence of CH. But if you work a bit harder, you could actually get rid of the minimal Ehrenstein lines. This model has been useful for a number of results, and it's essentially a model in which some consequences of PFA hold at the same time as CH. Right? So there's some consequences of PFA that are compatible with CH, and they have this feature that if you put the two of them together, put these consequences in a model of CH, that it will rule out the existence of minimal Ehrenstein lines. Okay, so this has mostly been just a discussion of minimal uncountable linear orders, but what about orders which are minimal with respect to being non-sigma scattered, right? So real types and Countryman types could be such examples, but you might ask, is there a linear order which is non-sigma scattered, and it's non-sigma scattered for a reason other than that it contains a real type or an Ehrenstein type? So that brings us to Baumgartner's example. Are there non-sigma scattered orders which don't contain real or Ehrenstein types? So Baumgartner let C alpha in S be a sequence of ladders, right? So S subset of some cardinal is stationary and consists of ordinals of countable cofinality. And C alpha subset of alpha is cofinal and order type omega. All right, so if you take the set of C alphas and you order it lexicographically, this is non-sigma scattered. Yet every suborder, every uncountable suborder contains omega 1. Right. So in particular, it's not Ehrenstein, it's not a real type. And it also has a feature that this example is inherently non-minimal, because you can always take the stationary set and split it into two stationary subsets. And if you decrease the stationary set properly, meaning that you throw away more than just a non-stationary subset of it, then the resulting suborder doesn't contain a copy of the original order. That is, you have to, for these examples like Baumgartner constructs, the isomorphism type of the linear order kind of remembers the stationary set, at least the stationary set up to non-stationary equivalence. And this example also has it raises a number of questions, right? So can you find an example which could be minimal, right? This one cannot be minimal. And is it possible that any non-sigma scattered order contains a suborder of size Aleph1? Is it possible that there are non-sigma scattered orders which don't contain examples like Baumgartner's? They don't contain real types or Ehrenstein types. So this is where a result of myself and Tetsuya Ishu comes in. We showed that under PFA plus, any non-sigma scattered order either contains a real type, a countryman type, or Baumgartner's example or its reverse. And this is, of course, for some choice of ladders, some S subset of omega 1. So in particular, any non-sigma scattered linear order contains a non-sigma scattered suborder of size Aleph1. And the only minimal non-sigma scattered orders are the real type and the countryman type, because the other ones can't, right? This Baumgartner's example can't be a minimal one. And if you contain Baumgartner's example, you can't be minimal. It's also true, Hossein Lami Ramandi and myself proved that if there's a supercompact cardinal, there's a forcing extension with no minimal non-sigma scattered orders. Okay, so the nagging question after all of this is, Ishu and I kind of worked fairly hard for this result, and in particular, just the proving that you had this reflection, that any non-sigma scattered order contained a suborder of size aleph 1, we had no idea whether, well, some of this, we had to use the strong axiom PFA plus, and it wasn't clear whether some of this was just a theorem of ZFC, right? Maybe it's just always true that any non-sigma scattered order either contains a real type, an Ehrenstein type, or Baumgartner's example. Maybe they always contain a suborder of size aleph 1. Maybe that's true at least if they're minimal. And in particular, it's a question, is there a consistent example of a non-sigma scattered order? Which is minimal and has cardinality kappa. Say kappa plus, which is greater than aleph 1. And so we answered, the answer that's yes, and this holds if B equals L and is forcible over any model. And this is the new result. This is with Eisworth and Cummings and myself. Now, there's a separate result that I mentioned on the first slide about Countryman lines and Diamond. And this a priori doesn't seem to have anything to do with this present problem. But the proof is actually quite similar, and it also is related to another question that was asked. So Baumgartner had a proof which said that this strengthening of diamond called diamond plus implies there is a minimal Suslin line. And I should note that this is also Daniel Sokup fixed an error here. So there was this mistake in Baumgartner's original argument, and Sokup provided a remedy for that. And Baumgartner asked, is diamond sufficient to construct a minimal Ehrenstein line? Is the result necessarily Suslin? It's actually, in Baumgartner's constructions, in some sense, quite surprising, because you would expect that if there's any analogy with the real types, in the presence of CH, there are no minimal real types, because you can sort of enumerate all of the dense subsets, the countable dense subsets, and all of the embeddings, and build suborders by diagonalizing. And it's natural to think if you have some strengthening of CH, that might help you construct suborders of a given Ehrenstein line into which the original one doesn't embed. And it turns out that that's not true. At least that's not true in general, because something even stronger than diamond actually allows you to build an ambient order into which such that it embeds into all of its uncountable suborders. And this example is a Suslin line. So we actually answer both of these questions by diamond constructs a Countryman line, which is necessarily non-Suslin, which is minimal. So yes, you can get away with just diamond in the construction, and no, the result does not need to be Suslin. So let's talk a little bit about how this goes. So we have, I guess, about 10 minutes left or so, and I'll just kind of outline the proof. So the construction. So diamond builds a coherent sequence of finite to one functions such that well, certain properties are true, such that one, every subtree of the tree of initial parts contains a sort of canonical subtree. This collection of canonical subtrees, there are only Aleph one of these. And two is that these canonical subtrees all contain, when Lex ordered, all contain copies of the original linear order. Okay, so I'm kind of being a little bit vague and about what I mean by this, and I'm kind of being a little bit sloppy, but in the interest of time, I don't think I want to flesh it out too much, but I want to elaborate on this a bit, and because I think this is the part of the construction which is kind of interesting. It's more interesting set theoretically. Okay, so let's forget about this. Okay, so suppose T is a tree, coherent tree, which is closed under initial parts. And consists of finite to one functions. So we have the usual ordering on T. And we also have a new order, which is, say, less than sub n. And this means that, okay, S is less than T in the usual sense. And if xi is such that, okay, the length of S is less than or equal to xi, and that's less than the length of T, then T of xi has to be at least n. That make sense? Okay.
Yes.
So, yeah. Okay, good. So a cone in T is a set of the form, the set of all T in T such that T is less than or equal to S or S is less than or equal to T. And a frozen cone is a set of the form, a set of all S, a set of all T and T such that T is less than or equal to S or S is less than or equal to sub n T. This is for some S in T and n omega. And so the theorem is really that diamond implies there is a coherent tree of finite to one functions let's see, such that T is closed under finite changes. Actually, not only that, but I'm cheating here a little bit. Yeah, let's say closed under finite changes. And every subtree of T contains a frozen cone. Okay, so the construction of this, and then the second part is really that if you take such a tree and you order it lexicographically, it will be minimal, right? It's relatively easy to embed T into these frozen cone trees when they're ordered lexicographically, and then you can show that under this assumption that every subtree contains a frozen cone, that the frozen cones with the Lex order embed into all of the suborders of T. Right? Now, I'm about out of time, but so this diamond construction is really what you get if you try to construct a coherent tree. You try to construct a Suslin tree of finite to one functions, which is coherent, right? That's an absurd request because no coherent tree of finite to one functions can be Suslin. It's easy to show that they have to contain an uncountable antichain. But this sort of argument that you read in Kunin's book of how to construct a Suslin tree using diamond sort of still seems to apply, right? It still seems to be that you can kind of guess your antichains or whatever, or subtrees, and then try to make good choices of what to continue and what not to continue at the limit stages based on what the diamond sequence predicts for you. And the insight is really that if you are building a tree of finite to one functions using this, what that argument adapts to give you is exactly this, that there's a coherent tree of finite to one functions, which is you can arrange as more over closed under making finite changes, and has the property if you take any subtree of your tree, it contains one of these particularly nice subtrees, one of these frozen cones. And I guess I will finish by going back to the very first slide and making an additional remark that Asaf Renault has shown that if you have a singular strong limit cardinal and 2 to the kappa, or a singular strong limit cardinal kappa, and 2 to the kappa is kappa plus, then square with diamond inside holds. This, or sorry, if you have, what do I want to say? If you have, if square holds at if square sub kappa holds kappa singular strong limit, and GCH holds there, right? Those are sort of 2 minimal things that you need in order to get this. You can upgrade them to this sort of square with built-in diamond. And it's known that, it's sort of well known that if in order to get a singular strong limit where square fails or where SCH fails there, that requires large cardinals. So, you know, if you have, if there are no minimal orders of cardinality greater than omega 1, then you must have an inner model with a measurable, for instance. So, which is kind of interesting. We knew, it isn't terribly surprising that something like that's true, but it was a little bit hard to prove it, right? So this tells you that in this result of, or at least some of these consequences of the issue Moore result, that you need some of the you need some of the large cardinal strength of PFA to get this result. Okay, I think that's a good place to stop. Are there questions?
Thank you, Professor Moore. Yeah, so does anyone have any question for our speaker? I just have one question. I'm not very familiar with PFA plus and diamond plus. What does the plus mean?
Okay, so first is the pluses are completely different. So okay. It's, I think that in both cases, the plus just means strengthening the principal sum. There's no sense in which you're doing the same sort of strengthening for PFA as you are for diamond. So what PFA plus says is that if you have a proper post set, you have Aleph 1 many dense open sets, and you have a name for a stationary subset of omega 1. Okay. Then there's a filter which meets those Aleph 1 many stationary sets and which interprets that name for a stationary subset of omega 1 to be really a true stationary subset of omega 1.
Okay, okay. And
and there's also like a plus plus, which means that you have omega 1 many stationary sets, names for stationary sets, and the PFA plus, PFA plus plus, MM plus, MM plus plus, these all hold in the standard models of PFA or MM. And the reason is that when you, like, how do you prove that? Well, you make sure that you sort of forced with the relevant forcing at some point along the way, and you add the generic filter for it. Those stationary sets, those names will actually be interpreted to be stationary because your filter is really generic. And then because the rest of the iteration is using post sets that preserve stationary subsets of omega 1, those stationary sets remain stationary at the end.
Okay.
So diamond plus, I'm going to give you a sort of cheap first approximation to it. Diamond is equivalent to saying that you have a sequence of countably many subsets of alpha for each alpha less than omega 1, such that for any subset of omega 1, there's stationarily many alpha where script A alpha contains X intersect alpha.
Yeah.
Okay, so if you can now naturally strengthen that to say, I want that there's a closed unbounded set of alphas where I guess your set correctly. That's what's usually called diamond star. And if you additionally ask for the set of places that you're guessing to be guessed as well, like for any limit point of your club, that like for any alpha, which is a limit point of the club, C intersect alpha is guessed by A alpha and your original set is guessed by A alpha, then that's diamond plus. I don't pretend that you would like internalize what that's really saying. But diamond plus is kind of what you need to construct a Carepa tree. And it's used in a handful of constructions that where diamond is not quite sufficient. Diamond plus holds a V equals L. And it's a sort of diamond on steroids, right? It just gives you a bit more control.
Okay, I got that sufficient idea. Okay, Luis Reyes, do you want to ask something? Hello.
Hi, Justin.
Hello.
We were like with some people discussing this. Now that you just answered the question about the PFA plus, do you have the same result that a super compact cardinal implies PFA plus, or do you need something a little bit stronger?
Or the consistency of so in any model, in any normal model of PFA, including just you do start with the super compact and you do the standard forcing construction, you'll get a model of PFA plus for free.
Oh, okay.
It is not true that PFA implies PFA plus, right? There are models which separate them, but you have to work to get them. It's not the other way around. And it usually amounts to carefully adding some stationary set which doesn't reflect, or adding, you do the usual PFA construction, but you somehow pollute it a bit by adding something else which witnesses the failure of PFA plus while maintaining that PFA holds.
Okay.
Yeah.
Thank you.
Okay. Anyone else has a question? Okay, if not, we thanks to Professor Moore for the talk.
Yeah, thanks for having me.
Thank you. Thank you.
And of course, people should feel free to email me after the fact if you have, questions that require more time, or that you don't think of them right away. Of course, always email me.
Okay, thank you, and thank you all of you for coming to our last session of this semester of this seminar. And well, we expect to see you again next semester, a different schedule for all of us. And thank you so much. See you next semester. And
yeah, see you later. See some of you.
days.
See you later.
Yeah.
I think many of you